All right, so what's going on, y'all? Now we're doing part B of 318. We have to determine the axial stress of the bar element. We only have one bar, right? They give us the modulus of elasticity, the cross-sectional area, and the length, and then as well as the global displacements, right? The global coordinates, U1, V1, U2, and V2. So let's go ahead and get started with this one. All right, so just like part A, right? The normal axial stress with respect to the global coordinates, this is the formula right here. So it's sigma is equal to C minus, I don't know the name of this matrix. I'm not gonna lie to you. So, but the point is, as long as we know what it is, that's all we need, right? Times the displacement vector. So C minus is E over L. It's usually EA over L, but since stress is per unit area, we don't include the area here. And then it's negative cosine, cosine, and sine. So this is the formula we're going to use to determine the axial stress in this bar element. So before we kind of assemble this equation here, we have to get our sine and cosine values. So cosine of 30, let me put step 2, right? Because that's really step 1. It's kind of knowing what you're going to do. So step 2, cosine of your angle, which is 30 degrees. Again, from the x-axis, that's the angle you always take. You're gonna have right here radical 3 over 2, and then sine of 30. You need sine and cosine, right, for this matrix, for this little, yeah. You will have 1/2. And now we could go ahead and start doing the equation, right? So step 3, let me make it a little lower right here. Step 3, you're gonna have sigma, right, is equal to this matrix right here, E over L, so it's 210, right? That goes to E right here. 210 times 10 to the 9. This is in newtons. A Pascal is newtons per meter squared. When you divide it by another meter, 3, right? Length. You're gonna have units of newtons per meter cubed. Okay. Then you multiply it by a dimensionless matrix, right? The cosine is negative radical 3 over 2. I'm just plugging in, right? Negative 1/2. Then we got radical 3 over 2. And then we got positive 1/2. And then we have our displacement vector. Displacement vector was given, right? U1, V1, which, this is in millimeter. You gotta be careful. So you gotta move this decimal over 3 times. For me, it's easier to move this 3 times than to convert this to millimeters and this to millimeters. It's just crazy, right? So I like to just do the displacement. So 0. Decimal starts right here, so there's going to be 3 zeros in front of the 25. Okay, that's just converting from millimeters to meters. 0 for V1, U1 V1, U2 V2, that is 0.001 and 0. Okay, and yeah, that's pretty much it. This vector here is in meters now. We converted it. So when you multiply newtons per meter cubed times dimensionless times meter, you will get the unit for stress, Newton per meter squared. So let's go ahead, and again, right, this is a 1/4 matrix, and this here is a 4/1, meaning when you multiply them, you will get a 1/1 answer. So it's just one answer that we're getting. So you get sigma, right, is equal to, let's leave 210 times 10 to the 9 alone for now, divided by 3. So you'll get this. Negative radical 3 over 2 times 0.00025. That's going to be negative 0.0002165 plus negative 1/2 times 0. So that's 0. Plus radical 3 over 2 times 0.001. That's going to be 0.000866 plus 1/2 times 0. And that's it. You might think it's going to be a small number, right? But nah, when you add these, yeah, you'll get a small number. But this 10 to the 9, it's really gonna amplify this thing. So this is steel. 210 times 10 to the 9 pascals. That's steel right here. So there's gonna be a lot of stress, even if it just deformed a little bit. yeah, just do the math, right? You will get sigma is equal to 45,465,000 newtons per meter squared. It's also a Pascal. Or you could simplify your answer, make it look nicer, 45.47 megapascals. And I forgot to mention it in the other problem. This positive number means that this bar is in tension. Now this is how I'm gonna prove it to you, okay? So hopefully I explained this correctly. Really wish I did in the other video, but I don't feel like redoing it. So look, this equation, the only thing you gotta take my word for is that this equation here, this given theory is correct. This is from the book, so it really is correct, okay? So look, this is what happens. Look at our original displacements, right? They determined that this is how much it displaced for x1, x at node 1, and x at node 2, right? v1 and v2, they stayed the same, 0, 0. So what that means is u1 moved along the positive x-axis. So you could see we're compressing it, right? Relative to v2, assuming v2 is still, right? We're kind of pushing it that way, 0.25 millimeters, so it's being compressed. Okay, so that's right here. U2 is moving 1 millimeter to the positive x, meaning this way, it's moving a millimeter. That's what they determined, right? They just gave us these numbers, we're taking their word for it. So what that means is when you plug them in here, right, U1 and U2, this negative will mean, multiplied by this positive means it's, well, obviously it's negative, right? So that means it's in compression, you're compressing it. So that's why I guess this theory makes sense. The way they derived it, you got to read the book, right? But this will fix everything out, assuming it's correct, obviously, right? So let's just assume that U1 was negative. U1 is now being stretched this way, right? So that means when you multiply a negative times a negative, you will get a positive number here, which is gonna pretty much increase our stress, right? If you're adding these two numbers, you're gonna increase stress, as opposed to, in this case, we're subtracting them. But yeah, that's pretty much it. So it's kind of the way you gotta see it, right? If you were to switch U2, now imagine U2 goes negative, this here would have been a negative, but this here's a positive. This will always be positive, unless you have negative angles, right? But that's totally something different. Let's assume this is the case, just for a positive 30. You will have a negative number here, which is gonna decrease our stress. So that's this means tension, just FYI. And a negative number will mean compression. I just want to explain to you what's going on behind this theory here, but just FYI, positive tension, negative compression. And yeah, that's the answer.